So now we'll be going over computing for medicine and some quiz questions. So two hospitals exchange allergy information using FHIR. And what is the full form? FHIR stands for Fast Healthcare Interoperability Resources, right? So one system interprets penicillin allergy as a drug intolerance instead of an allergy. Most likely issue is that this is a semantic interoperability failure. Why? The syntax FHIR is fine. The message arrives, but the meaning got interpreted incorrectly, right? That's a classic semantic mismatch. Different code binding, different concept chosen, or local mapping inconsistency. It's not just human error or process. It's that systems don't share the same coded meaning for penicillin allergy. Fix bind allergy intolerance.code to a canonical terminology, that is SNOMED CT allergy concept, and verify the mappings. Now, a friend you have thinks that EHR is scanned PDF of reports, but actually EHR stands for electronic health records. Correct them. Which statement is correct? So electronic health record is a repository in a computer processable form with a standardized model. And EHR stores structured, coded, and queryable patient data, for example, demographics, observations, problems, medications using models, for example, FHIR resources. A scanned PDF is an image, not machine processable, and loses computable semantics. EHRs enable decision support, data analytics, and exchange beyond being paperless storage. Now, clinician shares dataset on Google Drive, no DOI persistent data, metadata is missing, link breaks on ownership change. Which FAIR principle most violated? That is findable. Findability requires persistent identifiers, DOI, PIDs, process IDs, persistent IDs, and metadata that allow discovery. Now, broken links and missing metadata make the dataset hard or impossible to reliably find later on. Accessibility is related access control, but the immediate biggest violation is findability. And FAIR principles, basically the full form of FAIR is findable, accessible, interoperable, and reusable. Now, study combining two hospitals. One uses ICD-10 and the other SNOMED CT. Essential technique before integration is ontology mapping. So why you must map codes between code systems ICD to SNOMED, either using standard mappings, for example, WHO ICD maps, or custom concept maps to identify equivalent concepts. For example, diabetes diagnosis. Other choices are encryption, DID, NLP are necessary in general, but mapping semantics is essential here. Now, moving on, Simpson's paradox occurs because the overall effect reverses relative to subgroups caused due to confounding variables. So Simpson's paradox is driven by a lurking variable, that is a confounder, that changes group composition and direction of association, not random noise or duplication. Always check stratified analysis. Now, which statement is not true about retrospective versus prospective study design? So it is more expensive as compared to prospective studies is not true. Retrospective studies are typically cheaper, use existing data. The other limitations listed, selection bias, data quality, and difficulty establishing temporality, are valid for retrospective designs. For example, we have to give an example of confounding. Options include coffee linked to lung cancer because coffee drinkers smoke more. So coffee drinking is associated with lung cancer because coffee drinkers are more likely to smoke. Smoking is a confounder. Affects both coffee drinking prevalence and lung cancer. Randomization would remove confounding, which is not true about human physiological systems. So the answer is highly optimized, right? Biological systems evolve. So they are robust and adaptive, but not guaranteed to be globally highly optimized. They exhibit trade-offs, redundancy, and suboptimalities due to evolutionary constraints. The other three statements, that is, are self-organizing, basically exhibit self-organizing behavior, are have non-linear properties, and adaptivity are core properties of physiological and biological systems. In a directed acyclic graph, smoking, lung cancer, asbestos exposure, asbestos is actually a parent node. So asbestos exposure points into lung cancer. It's a direct cause node, so it's a parent of lung cancer in the DAG. It is not a confounder here because it does affect smoking. Confounder would affect both exposure and the outcome. Now, radiology AI trained on one scanner drops performance when new scans use different file formats or resolution. Example of an interoperability challenge, that is domain data heterogeneity or distribution shift. The AI fails due to differences in data representation or acquisition across systems, across system interoperability, or a domain shift problem. Now, which is structured healthcare data? X-ray images, doctor's notes, BP readings, MRI scans. Answer is BP readings. BP readings are numeric, timestamped, tabular, directly usable by statistical models. Images and narrative notes are unstructured or semi-structured with metadata and require processing. Policymaker sees obesity rising with smartphone use and concludes smartphone causes obesity, error due to confounding. There may be a third factor, diet, socio-economic factors, confounding smartphone use and obesity. Now, workflows are a part of process interoperability. Workflows define how information is used in organizational processes, that's process or organizational interoperability. Which best explains why EHRs are better than paper records? Because they allow structured storage, interoperability, and analytics. They enable computable data, CDS, analytics, cost security, and doctors still remain. Biggest challenge using unstructured healthcare data, it lacks a predefined organization. Notes and free text lack schema, they must be parsed, normalized, and NLP processed to turn into features. Not always inaccurate, cannot be digitized or useless for AI. Those are false. Right. Now, what is an ontology and how is it different from a simple data dictionary? Explaining this, draw a small ontology graph for 4 medical terms using is-a-has-a process. Definition: basically, an ontology is a formal, explicit specification of a set of concepts in a domain, their properties, attributes, roles, and the logical relationships among them, usually expressed in a way a machine can reason over. Description logic. It encodes intentional knowledge, meaning constraints, axioms, descriptions, not simply labels. Difference in difference with the data dictionary. So data dictionary contains lists, fields, types, permissible values, and textual descriptions. It's a structural artifact for implementation. But ontology models conceptual semantics, hierarchies, is a relation, has finding site, causative agent, constraints, and axioms enabling inference. Ontology supports reasoning and semantic relationships. Right now, data dictionary knows condition code is an integer. Ontology knows that myocardial infarction is ischemic heart disease, and that finding site must be heart structure. Right now, this is the example. You can go through it. SNOMED CT concepts are more than terms. List two essential properties understood by a fully specified name FSN. So two properties: unique language independent machine readable identifier. So each concept has a SNOMED CT identifier with a numeric ID so that it is readable by the machine that we are using. That is canonical machine reference for that meaning. The fully specified name is an unambiguous human label for that concept. It ensures that the concept that we are referring to is basically refer to that concept regardless of display labels or synonyms. Store IDs, not labels in EHR. Then defining relationships that support classification is a plus attributes. A fully specified concepts FSN implies a set of defining relationships is placed in the is a hierarchy and essential attributes which are sufficient to uniquely identify it. And it has a suffix which includes the primary hierarchy of that particular disease or disorder. So this is the suffix, right, of myocardial infarction. It maps to concept ID. For example, this the concept is a parent ischemic heart disease and defining attributes that mark it as an acute myocardial necrosis event. These properties enable both human clarity and machine inference. Now, why possible fracture of arm and patient is recovering well are not valid SNOMED CT concepts? Break them down via postcoordination. So why they are invalid? So SNOMED concepts are intended to represent precise clinical meanings. Phrases like possible fracture of arm are contextual, qualified, uncertain, or clinical impression or status statements that is subjective, not atomic, fully specified clinical entities. SNOMED models finding context, certainty, and status using attributes or separate concept qualifiers. So we post coordinate these ideas rather than inventing a single pre-coordinate concept. So how do we express them in post coordination? Notation used informally is concept name, the attribute, and the value. These are conceptual examples, not exact SNOMED IDs. Right. So base concept, fracture disorder, finding site, arm structure or specific bone, radius, ulna. Finding context or uncertainty, possible or use clinical finding with uncertainty attribute. And post coordinate expressions have multiple SNOMED CT IDs or clinical IDs. Right. Moving on. Predictive model for ICU patients, data types most usable for classical stats, how to use unstructured nodes. So we have these three options: blood pressure readings, X-ray, CT, and MRI images, text notes capturing patient history, progression, and treatment. So we need to classify them firstly as structured, semi-structured, or unstructured. So BP readings are structured, numeric time series, systolic, diastolic, with timestamps and units, mmHg. X-ray, CT, MRI images are semi-structured or unstructured. The image pixels are unstructured. The DICOM wrapper carries semi-structured metadata, timestamps, modality, study description. Practically treat imaging as unstructured for ML feature extraction. Metadata is semi-structured. And then we have text notes, history, progress, unstructured, free text. Though clinical notes contain semi-structured sections, right? Now, which is most directly usable for traditional statistical models and why? Structured data, blood pressure readings, because traditional statistical models using logistic regression or linear models expect tabular numeric categorical features. Structured numeric variables can be directly input without heavy preprocessing. Then approach to use unstructured data, notes for predictive modeling, detailed plan. High level pipeline is this: governance and privacy, IRB approvals, data use agreements, secure environments, de-identification of PHI in text, names, IDs, dates using clinical DID tools or controlled environments. Then we have data extraction and cleaning, extract notes and metadata, note type, author timestamp, normalize encodings, UTF-8. Then section segmentation, find history, exam, assessment, and plan. Many models perform better if sections are separated. Then we have annotation and label creation, create gold labels, outcomes from structured fields, mortality, ICU length of stay, ventilator need. Avoid label leakage, labels derived from the same node. Then we have NLP processing, tokenization, sentence segmentation, clinical specific tokenizers, lowercasing, punctuation handling, orthographic normalization. Then expand the abbreviations, for example, SOB stands for shortness of breath. Then entity recognition and concept normalization, named entity recognition, NER for diseases, meds, procedures, or vitals. and use either rule-based or machine learning. Map extracted entities or two terminologies, SNOMED CT, via string match, dictionary lookup, or tools. Post coordination when needed. Then feature engineering, bag of words, TF-IDF for baseline models, word embeddings, word2vec or Glovec trained on clinical corpora, right? Then contextual embeddings using BERT, fine-tune BERT for richer representation, entity level features, temporal summarization, then modeling choices, classical methods, logistic regression, XGBoost on engineered features, great when tabular plus engineered features, then deep learning, fine-tuned transformer encoders, and adder classification head, works well for text-only tasks. For long notes, use sliding windows or long former. Then we have multimodal fusion, combine structured vitals plus imaging features plus text embeddings. Fusion strategies, early fusion, concatenate features and train one model. Late fusion, train separate models and then ensemble, that is combine them. Or cross attention, more complex architectures to let modalities attend to each other. Then we have the image pipeline, reprocess DICOM images, windowing, resampling, use pre-trained CNN backbones, ResNet, DenseNet, adapted for medical imaging, maybe using transfer learning, extract the imaging features, then use when clinical, then fuse with clinical features, then evaluation and validation, hold out test set from separate hospitals, time periods to evaluate generalization, then use metrics like area under AUC curve, right? AUROC, AUPRC for imbalance tasks, sensitivity, specificity, decision curve analysis, then robustness and deployment considerations, and that's it, right? Pitfalls to avoid: label leakage, deriving outcome labels from the same free text note used as the input. Bias or fairness: a note language can reflect clinician bias. Model may encode it. Then class imbalance: use resampling, focal loss, or appropriate metrics, right? And that's it. And then you can go to this. This is a quick practical cheat sheet. There is findable, accessible, interoperable, reusable. Interoperability layers we have in increasing complexity. First we have syntactic or technical, then semantic, then process or organizational, then human. SNOMED core, concept ID, machine readable IDs required which are unique and unambiguous. Then descriptions, FSN, then the preferred name and the synonyms. Then relationships is an attribute. Then ref sets, FSN is unique, unambiguous name per language. Pre-process post coordination. Pre has a single concept ID or code. Post has composed basically multiple IDs in combination with attributes. Use post coordination for long tail detail, and that's it for this video.